Hmm? Yes? Okay, today we start chapter 4 about the n factorial garden. Analog of the Catalan garden, but with the exponential generating function. So first we start with permutation, something very classic. Classic things about permutation that everybody should know. Very classic. So there is different representation of permutation. Sometimes definition of permutation as a bijection from finite set to a finite set, which I can take 1 to n. So you can write this bijection of map 1 go to 4, go to 2, go to 3, 3 go to 9, etc. And this representation, in fact, it's in the language of B species. I don't consider any order on the number 1 to n. And this map also can be written in a cycle notation, where 4 go to 7, 7 go to 1, 1 go to 4, and you have this cycle notation. So this is permutation as a B species. Now you can say permutation as a L species is going to be a total order on the element or a word. I can see permutation as a word in the letter 1 to n. All letters appear once and only once. And I will use also, especially for Robinson-Stenstedt-Knuth correspondence, I will use a graphical representation like this on a grid. You put the point I, sigma of I, which means that you have an n by n grid, and there is one point and only one in each row and in each column. So this is another way to see permutation. So permutation, they form a group, which is called the symmetric group. So you know the composition, the product of two permutations, the composition of the map. If you have two permutations, sigma and tau, then the product is just the composition. 1 go to 2 by sigma, and then 2 go to 2 by tau. For example, 4 go to 1, 1 go to 3, so 4 go to 3. Composition of two maps, product of permutation. And this makes a group of the neutral element, which is the identity permutation. What happened?
They act on the right.
Yes.
Yeah, sigma
Yes.
first and then
I
tau
don't,
acting on sigma.
yes, but I don't do the usual way you will see in all this class. Sometimes I make operator from left to right. That's a word. It's but you can translate in your own way of looking. So there is the inverse of a permutation. You just take this permutation and you reverse the blue and red numbers. For example, 2, 3 becomes 3, 2. You just reverse the colors, and then you put a total order on this, and then you get this. It's like some card with 2 numbers in each card, and you reorder this blue number to get this. This is inverse permutation. So this is a group, the symmetric group with n factorial element. So a classical bijection. First bijection on permutation, all bijection, classical, very classical. It's you are going to transform permutation written as a cycle notation into a word in the following way. So you have your permutation, and you take, in each cycle, you take the minimum element. And then you are going to break each cycle, and to get this word, so this word, you order the cycle by the minimum element in decreasing order. So you have 6, the biggest of this minimum element, then 5, then 2, then 1. Okay, you put the minimum element of each cycle in decreasing order. So this gives you an order of the cycle. And then for each cycle, you transform a cycle into a word. You start from the minimum element, and you do this, 2, 3, 9. You read the cycle. So this is a cyclic word, but now you take one of the conjugate. We have seen this with the Lagrange inversion, etc., etc. So you break the cycle here. You start with 2, and you make a word 2, 3, 9. For example, here 6, 8, 6, 8. You see 1, 4, 7, 1, 4, 7. So each cycle is broken. There is a total order of the cycle, and you write the broken cycle into a word. You concatenate everything, and you have some block. And I claim that this is a bijection, transforming the cycle into a certain word with certain block. But if you forget all the block, I can reconstruct my cycle decomposition. So you start with a word with distinct letters. Then you take what is called very classical object. This is a left to right minimum element. I will call this LR, left to right minimum. So letters xi is a left to right minimum element if and only if xi is the minimum of all the letters x1, x2, xn. For example, there is 4 minimum elements, left to right minimum element. For example, 2 is the left to right minimum because on the left, all the values are bigger than 2. 3 is not because there is a 2 on the left. Okay, so all the value on the left of this element in purple circle, all the values on the left are bigger than the element. So this is the definition, left to right minimum element. Sometimes it's called also outstanding element of the permutation. And then to reconstruct the cycle notation, you take the left to right minimum element, you cut each in its block, and then you reconstruct the cycle by taking, for example, you take all the letters from the minimum element to the right, 2, 3, 9, and then you reconstruct the cycle this way. So this is the bijection. So the cycle of the permutation becomes the left to right minimum element of this word. And so the distribution of left to right minimum element are the same as the cycle. We have seen in the previous chapter that this is a Stirling number first kind, the smallest s, which we have shown that the distribution of Stirling number are like this. What was the proof? It was given by this. You remember the geometric function of permutation, each cycle was weighted x, and if you expand this, maybe I go fast. Last time I did not show this, but if you expand this, then you get this formula. So by calculus and working with spaces and weighted cycle, you get this formula. But today we are going to see a direct proof using some bijection of today. Direct proof that the left to right minimum element are given by this very simple polynomial. So this is what we have called last time binomial type polynomial. So this is also left to right minimum element. So exercise. A very simple exercise for computer scientists, or for very, very beginner in computer science. The first maybe program you can make in computer science is you have a word with distinct letter and you want to find the minimum of the word. So you are going to read the first letters and then you read all the letters from 1 to n, and each time you find a letter less than the minimum, then you replace minimum by AI. So this algorithm, this is a typical, very, very simple algorithm, gives you the minimum element. M is the current minimum element, and you want to have the cost. What is the average cost of this algorithm? So what is the cost? The cost is you have to read n times each letter, so maybe it's some constant a and b, and then the cost is each time you replace m by ai, so the number of your time you replace the current minimum will be exactly this parameter, number of left to right minimum element. So what I want to have usually in computer science is to have the average cost. So I have to make the average of the Stirling number. If I want, this is typically an analysis of algorithm, and usually people, you take a random word, a random permutation, and what is the average number of left to right minimum element? So this average number of left to right minimum element is given by the generating function. So this is a typical example of the average cost. Is going to be exactly this. Each time you have if you have k left to right minimum element, the cost is k and divided by the n factorial. So this gives you the average cost, the average number of left to right minimum element. So this is exactly if I take the polynomial Sn of x, the previous polynomial. This is S prime of n for the value x equal 1 divided by Sn of 1. Where Sn, you see, is this polynomial. So this is the logarithmic derivative of the polynomial. So it's the product of the logarithmic derivative. And so this quantity, the average cost, is exactly this number. And we will see in the next bijection. This is obvious. You will see immediately that this is the average number of left to right minimum element is this. This is called the harmonic numbers. And if you are specialist in computer science, especially reading the book of Knuth or the book of Sedgwick, etc., you will see many times harmonic numbers. Everywhere in the analysis of data structure, when you compare the key in the element, there is always the harmonic numbers appearing, and this is one of the reasons. So this is very simple algorithm, very simple example of analysis of algorithm, average, and using a geometric function or polynomial like this. So the average cost is this, and the minimum and maximum, sometimes people want to know what is the minimum, what is the maximum, and what is the average. Minimum number of left to right minimum is 1, maximum is n, and the average is hn. Hn is equivalent to logarithm of n. So we are typically in the field of data structure, computer science, data structure. So, in other words, a left to right minimum element means on the left, if you take this point will be left to right minimum element, if and only if, in this corner there is nobody, no black point here. But I could have taken the right to left also, so it means there is nobody here. Or even I can take the left to right maximum, there is nobody here. And right to left maximum. In fact, there is 4 different notions of outstanding element. There is nobody less than the point, nobody less than the point on the right, or nobody bigger than the point on the left, nobody bigger than the point on the right. So in fact, sometimes we will need to go here, but all have the same distribution, the Stirling number. In French, sometimes it's called by the French outstanding element. Now another notion is the notion of rises and descent. So take a permutation like this one, and a rise, it's at the index I, it's such that sigma of I is less than sigma of I plus 1. Like this one, 2, at this index, 1, 2, 3, 4, 5. For I equal 5, sigma of I equal 2, sigma of I plus 1 equals 3, so here there is a rise. I put the rise in red, and the descent in blue. So sometimes we say there is a rise at index I, or there is a rise at the value sigma of I.
Typo. Greater than sigma I descent.
Yeah. Descent should be greater.
Yes. Good. I see everybody is following very carefully. So replace this by greater. And so if and this one, there's nobody at the left, so we don't know what 6 is not. But usually we have to distinguish. There is a descent on the value 9, or there is a descent on the index 4. And let's call the distribution. I want to have the distribution of rises in the n factorial permutation. So let's call A and K the number of sigma of permutation having K rises. And this defines a polynomial, which is very classical. Again, it's called Eulerian polynomial because Euler, again, Euler was considering this polynomial for different reasons, other reasons than looking at the rises and descent of a permutation. 1755, something like that. So it's called Eulerian polynomial. And that was the first time bijective combinatorics was starting with Soutsan-Berger and Foata, and they have a lecture note in Polynôme Eulerien in French in 1978. It's a book in the lecture note. It has been republished in the Séminaire Lothar-Engel Combinatoire. So this is typical bijective proof. In their memoirs, they show, for example, a bijective proof of this. The Eulerian polynomial is related to the Stirling number second kind, the big S. So this is the number of partition. Number of partition of n in n minus k block. Multiplied by factorial means you order the block. So this multiplied by this means you have take a partition, take an order of the block. So in each block you are going to put the value decreasing, for example, and you hope that between two blocks, when you change the block, it's going to increase. But this may not happen. So there is this term. And so I ask you, exercise, find the bijective proof of this. It's going to be sign reversing involution. Because there is a minus here somewhere. It's not too difficult. But this is typically, this was in 70, almost 50 years ago, the starting of bijective quadratics. In this memoir also, they talk about secant number, tangent number, alternating permutation. And, so it becomes very classical combinatorics. So we'll use another very classical parameter in permutation is exceedance. We say that there is an exceedance on the index I if I is strictly less than sigma of I. This is strict exceedance. If you allow to have equality, then you have fixed point. This can be weak exceedance, but I will strict inequality. So for example, this permutation here has 5 exceedants. 1 is strictly less than 4, 2 is strictly less than 3. But you see there is a fixed point, and this is not an exceedance. I call x of sigma the number of exceedants. This is another parameter on permutation. And then the distribution of this parameter exceedance among the symmetry group is exactly the same as the distribution of rises. And so it is the polynomial enumerating exceedance is again the Eulerian polynomial. Same polynomial which enumerate rises or which enumerate exceedance. So it's very classical, and there is a bijection to show this, that they have the same distribution. So I go back to the previous bijection with cycle becoming a word with a left to right minimum element. So what are the exceedants? You see the exceedants, for example, 1 is less than 4. In the cycle, when you have the arrow, means say 1, 4, 4, 7. So I put in red the 5 edges corresponding to the 5 exceedants of the permutation. Now if you look carefully, what happens of these 5 edges in the bijection with word, with left to right minimum element? So inside the block, the 2 go to 3, 3 go to 9, these edges are preserved. But then I claim that the number of edges in red inside the block, where there is a rise, is exactly the same, correspond to the number of edges in the cycle where there is exceedance. So you have to check something. You have to check that between two blocks, when you go from here to here, there is not going to be a new rises. But this is because this is the minimum element of something, which is in here we have the. I should show this example. From this to this minimum element is less than this one, and all the value here are bigger than this. So this big value is bigger than this one. So there will be always a descent. And then you have to show also when this edges, when you break it, there is no example, but if it was an exceedance, if 7, for example, if going, no, it cannot be an exceedant because it's a smallest value. So these edges here cannot be exceedant because they disappeared in the process. So you convince yourself that the exceedance here is going to become the rises of this word. So I have the same distribution. Exceedance becomes the rises of the permutation. Okay, we are with rises and descent, and now the up-down sequence of the permutation. We have seen already this notion with the alternating permutation. The up-down sequence, the sequence, it's a word in n-1 letters, going up or down. It's a sequence of rises and descent. So this is a word, you see. It's a word with 2 letters of length n-1 if the permutation has length n. And for example, we have seen tangent and secant number are enumerated by alternating permutation. Alternating permutation means you have a descent, rise, descent, rise, descent, rise. So the word in the up-down sequence is constantly alternating. There is no rise, rise, double rise or double descent. What we call double rise is twice, two rises consecutive, or double descent, two descent consecutive. Exercise. Find an algorithm. Even there is some formula, but there's an easy algorithm to compute the number of permutation with a given up-down sequence. So I show you the algorithm, and the exercise is to prove that this is correct. So I give an example. Rise, descent, descent, rise, rise. So you make a tableau of numbers. You start with 1. Then the second row is you look the first value is the rise. So you put on the left of this column, you put a 0. And you do the following: 0 plus 1 equal 1. Then I have a rise. So you take this number, you put a 0 on the right of this column, and then you do the following: 0 plus 1 equal 1, 1 plus 0 equal 1. So it's a kind of analog of the Pascal-Pingala triangle. It's a modify rule. Sometimes I add from left to right, sometimes from right to left. So again, a descent. So you shift by 1 and you put a 0 here. So 0 plus 0, 0. 0 plus 1, 1. 1 plus 1, 2. Now I have a rise. So I put a 0 on the left. 0 and 2, 2. 2 and 1, 3. 3 and 0, 3. 3 and 0, 3. Again, rise. So 0 and 0, 0. 0 and 2, 2. 2 and 3, 5. 5 and 3, 8. 8 and 3, 11. Total number here, 26. So I claim there is 26 permutation having this up-down sequence. So the exercise is to prove that this gives you. And what means the number here? It's going to count the number of permutations the given up-down sequence according to something. I give you the hint. I am counting the 26 permutation according to the value of the last letters.
So in fact, you could also use it to give a generator for the permutations with a given up-down sequence.
A generator? What do you mean?
To list each of them exactly once without repetition.
Mm-hmm. Each one is counted exactly one, yes. So you can impress your friend. Now we know tangent T with alternating permutation. So look, you can do this. Alternating permutation. So you have this tableau give you the tangent and secant numbers. Let's take this row. Say 0 and 1, 1 and 1, 2, 2 and 0, 0. Or this row here, 0 and 16, 16, 16, 32, 46, etc. So you do the same algorithm, but with alternating 0 and 5, 5, 5 and 5, 10, 10 and 4, 14, 14, 16, 16. So if you take the sum of all elements in a row, you get, in fact, the sum of all these elements is going to be this one. So in fact, the tangent and secant number appear also at the. Here you have 1, 2, 16, 2, you have the tangent number, and here 1, 5, 61, the secant number. So you can do this, and computing tangent T, you see, in a very nice way. Knowing that tangent T and secant T are interpreted by the alternating permutation, the generating function for tangent and secant. So this is a way of computing. In fact, you can deduce from this that if you give an up-down sequence, what are the words which give the maximum possible permutation? And in fact, it's an alternating permutation. For a given word, the number of permutation with this given up-down sequence is maximum when the word is alternating. Okay, now we go to the garden of Q analog. So inversion table, inversion number, Q analog of permutation. So again, this is a very, very old subject, very classical. So I start with the real Q analog, the real interpretation of n factorial. I start with sub-accident function. A sub-accident function is a function f from 1 to n, all the number 1 to n, and it's more convenient to start with 0 and minus 1. I can put 1 n, but it's better 0 and minus 1 for the q reason. So, and such that for any index I, this function is between 0 and I. When I call f capital N the set of sub-excitant function, and obviously the cardinality of this is n factorial. Because for f of 1 there is one choice, f of 2, 2 choice, 3 choice, 4 choice. So in fact this is the most simple direct interpretation of n factorial. It's not permutation, it's this. To say that it's a permutation means you are going to give a bijection between permutation and this set of sub-excitant function. So in this class I will give two bijections between permutation and this set of sub-excitant function. So here is an example, you see, visual example of sub-excitant function. So this is this function. It's here is 0, 1, 1, 0, 2, 3, 6, 3. So you have 2 choice to put the black point, 3 choice to put the black point, 4 choice, 5 choice, etc. And then if I take the generating function of q power the sum of all the value of f of I, sum of f is the sum of all this number in red, sigma of f of I, and then I get obviously this q analog, because the choice of each black point are totally independent. So what is the generating function for one column? It's a product of generating function, and for one column it's 1 plus q plus q2 plus q3. This will give you q3. So for each column, this is the first column, second column, and the last column. This is the weight. So obviously you have this product. So this is the most natural interpretation of the q analog of n factorial. So sometimes people denote like this or like this. Sometimes you put a q, sometimes between brackets, and this is enough to say that this is q analog. So in fact the q analog of n factorial is a product of q analog of each numbers. We have seen this in the introduction to q analog with Catalan number in chapter 2. And so 1 plus q plus qi, you can write this as 1 minus qi divided by 1 minus q. So the q analog of n factorial is this product. So when you see from when you see this kind of product, then you are in the garden of q analog. This is a detection analytic way to detect q analog, and in the conventional way is a parameter which counts the area, which counts the sum of the instance when something happened, like we have seen the bonds, we have seen 3 or 4 q analog of a Catalan number. So you cannot say, for example, the Eulerian polynomial with a value with x is not q analog. The x analog, no, it's q analog. It's something reserved for this when there is this kind of formula associated to a parameter which is quadratic in. So I will give two bijections between permutation and sub-excitant function. So one very classical inversion table of permutation, and maybe less classical, an assembly of increasing arborescence. So first the inversion table. So we define the inversion of a permutation. It's any pair ij such that I is strictly less than j, and sigma I is bigger than sigma j. And the inversion number of permutations, the total number of inversion. So you can see this in a visual way. For each red point of the graphical representation, see there is a black point on the left and a black point below. So each red point corresponds to an inversion of the permutation. So the total number of red points is the total number of inversion of the permutation, and this is called by Lascaux the Rothe diagram. This was very old. And Rothe want to prove that the inversion number of permutation is the same as the inversion number of the inverse permutation. So he put this in a visual way, and taking the inverse permutation is just taking the symmetry, the diagonal of the diagram. So you have a visual proof of this elementary fact. So now it defines the bijection using inversion pair of the permutation. So what you do is the following, I define the following subaccident function. If I take a x, which is equal to sigma of I, so I take a value x, and f of x is going to the number of j such that sigma of j is less than sigma of I, and I is less than j. So I hope it's a good orders inequality. So it's this value, sigma of j is at the right of x, and it's less than x. So it's sigma of I and sigma of j is going to give you an inversion pair. So this is a function. You take x equal xi, and you must have this and this. So you count how many black points like this are in this position. So example, if I take this permutation, for each below I put in red, for each number, the number of value at the right of 6, for example, how many, and less than 6. So there is 3. 5, 1, 4 are less than 6. So below I put a 3. And then f, the value, the function f is the following. So 6, f of 6 equals 3. So you see this, you reorder for the 1, I take f of 1 equals this value, f of 2 equals this value, f of 3 this value, so you reorder this and get this inversion table, which is a subaccident function. In fact, there is many ways. This is called inversion table, because you can take by index, by value, bigger on the left, on the right, bigger or smaller, so there is 8 different inversion tables. This is one of the possibilities. You see, I take my permutation, I get this, and then I get f of x, and you get this subaccident function. Of course, it's a subaccident function, and I claim that this is a bijection. So another way to define this function f, for example, f of 7 is 4 because there is 4 black points at the right of this and less, so there is 4 black points in this quarter. And you see these 4 black points are in bijection with these 4 red points. These 4 red points correspond to these 4 black points. Each one is correspond to a black point. And so f of 7 equal 4. Let's check. F of 7. No, this is a different permutation. Okay, it's another example. Reverse bijection. You give me the inversion table, so you give me the subaccident function, and I want to get back the permutation. So I start with an empty cell. I put the 1, and this is going to be weight q power 0. So now putting the 1, I have 2 choice to put the 2, and I label the choice from right to left. So if my subaccident function f of 1 is 0, I will put it here. If f of 1 is 1, I will put the next one here. So f of 1 is 2. No, is 1. This gives me a weight q power I. Now f of 3, I have 3 possible choice. I label the choice 0, 1, 2 from left to right. And I choose one of the 3. So I choose the value of f of 3, of a subaccident function. F of 3 is 2. This gives me the 3 here. So you see f of 4 is going to be 0. I chose the first position. F of 5, I choose the last position. F of 6, again the last position. F of 7, the position number 1. You see, so each time you insert a new value, each time you open a new empty cell for the next one. Each time you put n, there is n plus 1 choice for the next one, and you label the choice from right to left. And you put your value, for example, 7 here, because f of 7 was equal to 1. If you know the subaccident function, f of 7 was equal to 1. And here I put the weight. You see, the index are the subaccident function. 0, 1, 2, 0, 4, 5, 6, 9, 2, 3. Total is the sum of all these different choice gives you q power 16, which is the q analog, the sum, which is the function sum of all the value f of x. So this, you can easily see that this is a reverse bijection, because each time you put a value, if I put the 8 here, I put in position 3, and on the right of 8 there is 3 numbers, and if I add some new numbers here, they will all be bigger than 8, so the number of inversion in the final result of 8 will be exactly 3. Okay, the index of the cell give you exactly the number of inversion at the end, which will be related to this value. The number of value at the right, which is less than this one, it's 3, and it will be invariant in the process because all the new value you add will be bigger than 8. And now if you look carefully, I have not only the Q analog, the inversion number, but I have also the left to right minimum element and right to left minimum element, because each time you take your choice at the minimum possible, each time f of x is 0, you get a left to right minimum element. See 1 and 4 here. So 1 and 4, you see, they are a right to left minimum element. The value is 0 and 0. And this is exactly the right to left minimum element. Now the left to right minimum element, it's 7, 6, 5. No, the 7, 6, 5, 1. So, no. 7, 2, 1. There is 3 left to right minimum element. 7, 2, 1, and you see that now the value of x is the maximum possible. So the value for the left to right minimum element, so it's the maximum possible, and it's a left to right minimum element. So now you can easily prove this, x plus 1, because each time you have the general polynomial is x plus 1 plus 2 plus I minus 1. So each time you take the first one, you put an x. If you take any other, you put the index I. So you can easily, this polynomial is a product of the polynomial which count number of times you touch the 0 level. Now if you can also make the double variation, number of times you take maximum, and in fact you get the double, there is 3 parameters. Each time you have the Q analog, each time you touch the leftmost, or each time you touch the rightmost, which corresponds to each time you touch the diagonal or each time you touch this one. So you can have a total explicit formula for the 3 variable parameters, the Q, and left to right element, and right to left element. So you have this polynomial, which is a polynomial enumerated one choice, one column. This is a minimum choice, maximum choice, and all of the choice with the Q. So you have a kind of beta gamma Q analog of n. So you have a beta gamma Q analog of n factorial. And so the Q analog beta alpha, or if here I change, I put alpha beta Q analog of n factorial is a product of this thing, you see. So it's very easily with inversion table. This is one column, the generating function for one column with 3 parameters, minimum choice, maximum choice, and Q power I when you choose the choice as level I. And we will use this next time with the Laguerre history and Laguerre polynomial and moment of Laguerre explicitly like this with them. So, now the MAJ. So we have seen last time MAJ, people ask why MAJ, because the major of McMahon. So here is this picture of McMahon, and he defines the MAJ of a permutation, and he shows that the MAJ of permutation, the distribution of the MAJ is the same as distribution of inversion. And this distribution of the sum for the parameter sum for sub-excitant function, the parameter inversion for permutation, or we are going to see the parameter MAJ, is called Mahonian distribution. So the MAJ of a permutation definition is the sum of the indices such that you have a descent at index I. Each time you have a descent at the index I, you put a Q power I. In fact, McMahon is famous also for his McMahon master theorem. which interprets the inverse of a determinant. So we will see in the class on heaps of PCs that there is a nice interpretation with heaps of cycles. And in fact, he proved this identity in the general case of not only permutation, but word with repetition of letters. And he used his McMahon-Master theorem to prove the equality of the two distributions, the general case of words with repetition of letters. So we are going to prove that to give a bijection, to give bijective proof that the inversion of permutation is the same distribution as maj of permutation. So we are going to repeat the same process as for inversion. You say you insert a new value. You have n possible cell, or at the level n plus 1 possible cell. I am at value 1 to n, and I insert a new value. There is n plus 1 possible choice, and the choice for inversion pair are labeled from right to left. This is the first choice, second, third, and each time you take choice number I, you put q power I as a weight. And the total weight will be q power, the sum of all the possible choice, index of possible choice, and this gives you inversion number. So I am going to do the same philosophy, same process, inserting each time a new value, but I just change the labeling of the possible choice. So the labeling is the following. When you are in the intermediate state of the construction, you have a partial permutation. So you can take the up-down sequence of the partial permutation, and you label the possible choice 0, 1, 2, 3. You first label the descent from right to left. So 0, 1, 2, 3, 4, 5 until k, the leftmost descent. And then you start the rises from left to right. So k plus 1, k plus 2, k plus 3, etc. So I'm going to label like this. You take a sub-accident function. Each time I label like this, and I claim that the sum of the value of the sub-accident function is going to be the maj of the permutation. If you take the sum of sub-accident function and do this, the sum of the value will be the inversion number. So the equality of the two parameters, say you start for the same sub-accident function. You do this, you take inversion, you get inversion. You do this, you take the maj. It's just a reordering of rewriting in a different order the possibility. So Amri, you have a question?
Yeah, no, I was just wondering you can define the maj of a partial permutation.
It's the sum of the indices of the descent. Any partial permutation there is an up-down sequence, and the maj is the sum of the indices of the descent.
But the index will change when you add.
Yes, each time. This is going to be, you anticipate on the proof. He's always anticipating on the next 2 or 3 slides. So let's do the construction. So I start with 1, and by convention I say there is a 0 at the beginning, a 0 at the end, because there is 2 possible choice for the 2, and this is the rise, this is the descent. So I label from first the descent, then the rise. Then I put my 2. For example, the 2, I put it on choice number 1. Then you relabel 0, 1, 2. I put the 3, choice 1. See, I put the choice. It will be, at the end, I will have q power, all the sum of all this. Then I relabel. Then I put the 4 in position 0. So you see, you can define the maj of this. It's the sum of the indices of the descent. What you have to prove is that each time you change a new value, the maj, the partial maj, is increased by this value. This is the key of the proof. So I relabel like this. Now I put the 5. The 5 has the value 2. The sub-accident function is 2. So I put 5 in the choice number 2. I relabel. So maybe the label of a single descent can be changed in the process. So 0, 1, 2, 3, 4, 5. Now the 6, I put in value 3. The 7, so you continue like this, relabeling, putting the 7. Here is your sub-accident function, the choice. one choice here between 0 and 1, between 0 and 2, between 0 and 3, etc. You have your sub-excitant function appearing here. And for this sub-excitant function, I construct a permutation. And I claim that at the end, if I take the Maj of this, which is the sum of the indices of the final permutation, I don't make by purpose, but this is alternating permutation. The Maj is 1 plus 3 plus 5 plus 7, give you 16. And now if you take the sum of this all possible choice, the sum of the value of the sub-excitant function, you get 16. So what you have to prove is that in the process, each time you have a new value, the new Maj is going to be increased by this value. And at the end, you will have this. So you see, from the same sub-excitant function, you can construct, by labeling the choice in a trivial way from right to left, construct a permutation such that the sum of the value is going to be the number of inversion, or you can do this labeling, and you will get the Maj from the same sub-excitant function. So two different labeling give you totally different parameters, the Maj and the inversion number. So you see the philosophy of history, you see in Q-analog. And history, you will see next time many history, Hermite history, Laguerre history, so this is related to. And last time we have very fast, I show you control theory. And control theory, there was an history constructing the tree related to a differential equation. So the philosophy is that you have some empty cell, and you put some new value in the empty cell. There is a certain number of empty cell. You put a new value, and then this new value is going to give some child to create some new empty cell. So according to a certain rule, here each time I have all empty cells are the same, I fill a new empty cell and I create two new empty cells. So at the time there is always one empty cell, two empty cells, three empty cells. But sometime you will see it next time on Thursday that some empty cell maybe I can close. The number of empty cell can increase, can decrease, and in differential equation it's much more. I can empty cell as a color can be blue, red, green, and then a green empty cell, when you fill up it creates two new cells which are red and blue. When the red is filled up, you blue and green. I am doing elliptic function. So you see the philosophy of this history. It's a sequence. You are constructing a commutative object with a sequence of primitive operation. Each primitive operation has a certain number of choice. So you label the choice in a certain way. And each time you do a primitive operation, then the number of possible choices is going to change according to certain rule, the color, everything. You can imagine many very complicated history. And the philosophy is that the Q-analog is each time you have a choice number I, it's Q power I is the weight of the Q-analog. And at the end, the Q-analog of the history is Q power, the sum of all the possible choice. So depending on the labeling of the choice, like here, Maj and Neve, you'd get two different Q-analog of the same commutative object. So now we go to the n-factorial garden with trees. So now it's less, we quit the very classical, all this I give you before was very, very well known, very classical, and now we go to increasing binary tree. So increasing binary tree is a binary tree where the vertices are labeled 1, 2, 3, 4, 5, n, and they go increasing when you start from the root until the leaves of the tree. Or in other words, any child of a father is bigger, as a label, bigger than the father. So we have already seen this before, but I just repeat. And there is a bijection between increasing binary tree and permutation. You just look the binary tree in order. First you read the left subtree, then the x, then the right subtree. So you define the projection of the increasing binary tree, and the projection give you a permutation. I just recall what we have seen in chapter 3 about differential equation, and the projection is a permutation. And this is the bijection between increasing binary tree and permutation. So the reverse bijection is the following. You start with a word of distinct letters, or a particular case, a permutation. Then the delta, we call it the déployé. Déployé is like a bird which opens his wings. The déployé of a permutation. So the déployé of an empty word is empty trees. And the déployé of a word, you take the minimum of the word. So you can cut the word in W equal U, M, V, and then the deployer is a binary tree related to this, is a binary left subtree, the roots, and the right subtree. So proposition, these two maps, the projection and the deployer are inverse each other. So I denote by Tn the set of increasing binary tree, sigma n the set of permutation. And then the reverse bijection, I define how I define how to say the left son of a vertex. If I take a vertex label X, what is the value of left son? If there is a left son or a left child, if there is a right child, what is the value? So I am going to give explicit expression of the left son and right son by the following definition. I take the X factorization of a permutation or a word. It's a unique factorization like this. So your word is split into 5 possible parts. So the letters of lambda of X and rho of X are all strictly bigger than X. And the length of these two words are maximum. So you see, you start, the letter X is inside, it's in the middle of the word, and on the left, you go on the left, taking all the letters bigger, strictly bigger than X, until you stop. Maybe there is no letter strictly bigger than, but so maybe this word is empty. But you take the maximum possible letters on the left of X, bigger than X, the maximum possible letters on the right of X, and then maybe there is some U and V appearing on both sides. So this is the X factorization. And lemma, so once I have the X factorization, then I can say what is the left subtree, the right subtree, and the root of the left subtree, the root of the right subtree. So the left subtree of the vertex X in the tree is exactly the deployer of this. And the right subtree is exactly the deployer of rho of X. So this means that the tree is related to this is the left subtree, and the tree related to this is the right subtree. And the root of these two subtrees is going to be the minimum element of this will be the root of the left subtree. So it will be the left son of X, and the minimum element of this will be the right son of X. I have not written this, but so this is related left subtree, right subtree, and minimum of this will be the left child, minimum of this the right child. If this is empty, then there is no right subtree. For example, if I take X equals 3, I have two right son, left son. So if you take 3, then the rho of X, rho of 3 is 5. So it's and lambda of 3 is all this 6, 9, 7, 8. So you have the deployer, the left subtree is all this, and the minimum of lambda of X is 6. So the left son is 6. Okay, here there is nobody. At the right, no, it's the last. On the left of 6, there is nobody, because if I take 6, lambda of 6 is empty. There is nobody there. So there is nobody on the left of 6.
So on the left it was the maximum increasing on the left of 3.
The left subtree?
Maximum that is greater than
The left subtree of 3 is this. Because of the lambda of X, if you look on the left, take all the letters bigger, strictly bigger than X. There is 4 letters, 6, 9, 7, 8. So all these letters, 6, 9, 7, 8, will be the projection of the left subtree. Or the left subtree will be the deployer of this word. And the minimum, 6, will be exactly the left son of Now there is a relation between the classification of vertex of the deployer according to the fact there is one child on the left, one child on the right, no child or two child. So there's a classification. Here it's a double vertex. This is a single vertex on the left, single vertex on the right. So this classification can be reflected in the permutation by what we call valley, double rise, double descent, and peak. So in red, this is the peak when you go up and down So 5, 8, 4 are the peak of the permutation. The valley or trough are in blue, going down and up. And then there is double rise, double descent. 6 is a double descent. Or there is a double descent on the index 3, or a double descent on the value 6. And here, a double rise, I mean, and here a double descent. I make the convention that there is a 0 at the end and a 0 at the beginning. So this will be a descent, and this will be a rise. So this will be a double descent. Even if there is only one descent in the permutation, this is a double descent. And I claim that this classification of in this 4 kind of this value is the same as classification in the binary tree. So peak corresponds to leaf of the binary tree. Valley corresponds to double vertex in the corresponding binary tree. Double rise corresponds to a single vertex going on the right, and double descent, single vertex going on the left. So I will need this in the following section, chapter, next time or next week. So for example, so this is another example at the beginning. The first lecture, chapter 0, was instead of defining the in order of the binary tree, I defined the projection. And projection, you can visualize it like this. You put the binary tree like this, but you have to shorten the length of everybody so that, and you see you get the permutation by projection of the binary tree. And this is really the word déployer. Déployer like a bird which opens his wings, and the déployer of a permutation gives you a binary tree. So this is a visual way to see the in order or the projection of a binary tree. Now let's see what happened on our nice parameter, nice left to right minimum element, the right to left minimum element. What happened? We have seen in the inversion table, we have seen the Stirling number. So what happened in this bijection? So I claim they are going to be related to the left branch of a binary tree. The left branch, or the principal left branch, is the left branch of the binary tree. See, this is the left branch. The maximum sequence of vertex is always going to the left, or the maximum sequence of the vertex always going to the right is the right branch of the binary tree. And this is going to be related to the left to right minimum element. So proposition, if you have a permutation, you have the related increasing binary tree, then the left to right minimum element of sigma is exactly the left branch. The vertices, the value are exactly the vertices of this left branch of the tree T, and the right to left minimum element exactly the vertices of the right branch. This is easy to see. You will just check, for example, you have this binary tree. The projection is this, and the left branch, 1 to 5, it's exactly 5 to 1, the left to right minimum element. And now the right to left is 3, 1, 3, 1, which is exactly the right branch of the binary tree. Exercise. Hook length. So hook length formula, the usual, are very difficult. There is one in we will see on the hook length formula for Young tableau, but here the formula is easy. Very easy to give this exercise. You want to count how many, you give a binary tree with n vertices, how many ways to put label on the binary tree such that the label go increasing. So in other words, how many increasing binary tree with B as the underlying binary tree. So how many ways to label the vertices of the binary tree such that the vertex go increasing when you go from the father to the child. And the formula is this. It's like a hook length formula. The hook are this. So the formula is n factorial divided by the product of the size of all subtree. So you take a binary tree, take a vertex S, the subtree is B index S. So take the size of the subtree, the number of vertices of the subtree. So you take the product of all this size of all the subtree, and this product divided in factorial. And I claim the ratio is exactly the number of ways to. So it's not too difficult to prove the. this nice formula, which is belongs to the so-called Hook-Lens formula. Another exercise, if you take, you cut the permutation in UV in two parts, and you know the deployer of U and you know the deployer of V. So you know the binary tree, increasing binary tree associated to U, you know this one. Describe a procedure to deduce this one from these two. And for people who are very well know about Hopf algebra of a binary tree of Loderenko, this is the key to understand this, the product of two binary trees. But I give you a hint to get the procedure. It may be difficult to imagine, but the hint is you get the inspiration to do this from proposition page 117 of the exercise on binary search tree, which I hope I have time to give you today. So there is some exercise about binary search tree. There is a proposition on the slides which is coming next. And from this proposition, you get the inspiration to construct the algorithm. The exercise is once you know these two trees, don't reconstruct everything, don't take the product, reconstruct everything. No, try to use these two trees and how they can merge, mix together to get the tree of this. And it's very related to this proposition I am going to give in the sequence of exercise on binary search tree. Today is a lot of exercise. So you will have food for the next 2-3 weeks. Now you have an exercise, you have a permutation. Permutation associated to an up-down sequence. Okay, permutation gives you an increasing binary tree. Below the increasing binary tree, there is a binary tree. And I think in the complement of a chapter related to Catalan number, we have defined the canopy of the binary tree. So the exercise is to show that this equals this. There is a compatibility in example. It's you have this this permutation with this up-down sequence. Down minus mean down, plus mean up. You have this increasing binary tree. What is the canopy of the underlying? You take this external edges and you look red, blue, red, blue. So you get exactly the same word. This is up-down sequence. This is a canopy, and they are the same word if you replace this red edges by a minus, which is a descent in the permutation. So it's a nice compatibility. There is 3 notions. This is the words with 2 letters. So this is counted by 2 power n minus 1. This is counted by n factorial, and this is Catalan numbers. So you have 2 power n, Catalan, and n factorial. So this is the 3 main. If I have time, I have a complement to show you that there is a permutation, permutaodred, associahedron, and the hypercube. So all this, there is process behind this. They are all compatible. There is very nice cometrics between these 3 things: 2 power n, Catalan, and n factorial. The second kind of increasing trees, now we go to arborescence, increasing planar tree, or in fact it's a species of arborescence, and an assembly of increasing arborescence has been bijection with permutation. So here is a permutation. You get the increasing binary tree related to the permutation. You know the rotation of binary tree. This was to transform binary tree into a forest of planar tree, but I do the rotation with keeping the labeling. So this gives me an assembly of increasing arborescence. If I forget the order, between each vertex, this is an arborescence in the sense of species, and this is an assembly of arborescence, and they are increasing. So I am in L species. So if you take an assembly of increasing arborescence, you can always put the sun in decreasing order. If you want to go back to this picture, the sun has not order in arborescence, but if you put the sun in decreasing order, then you can go back to this tree and get the permutation. So now easily you can go from this to this. From an ensemble of arborescence, you can go to this permutation. Just look, if you put each child of a vertex in decreasing order from left to right, so you read this in prefix order. So suppose there is a 0 here, so you go to 4, go to 1, 6, 9, then 7, 8, so you 3, 5, and 2. So you follow your tree like this, like we are doing in planar trees. But from our arborescence to get a planar tree, you just make the convention that the vertex are in decreasing order. So you can get this permutation and this diagram commute. Now from this you get a sub-accident function. Very easily, it's trivial because 5 go to 3, 3 go to 1. So this kind of picture is a sub-accident function. 6 go to 7. Oh no, 6 go to 1, you see 6 go to 1. So this is a sub-accident function.
And the roots go to 0.
And the root, yes, is 0. In fact, there would be a 0, an extra vertex. As we are doing from a forest or planar tree, we are always doing a planar tree. Forest was of size n and planar tree of size n plus 1. So now you can, using this, you can go from this to this, or from this to this directly. So this means exercise give a direct definition of this bijection. So that's the diagram commute. So exercise you have to make some exercise you have to imagine. You have to show you have a good imagination to get a direct definition of this bijection. Okay, so this is all the garden of botanical garden of trees, forests, all this in the n factorial world instead of the Catalan world. Another exercise. I told you today is the exercise lecture. So exercise, take a 1-2 arborescence. Definition is such that every vertex has only one of two child. Now give a differential equation satisfied by 1-2 increasing arborescence. I don't give you proof that this object satisfies this differential equation. No, you have to find the differential equation. And then from this, you will deduce that the number of 1-2 increasing arborescence is exactly given by tangent and secant number according to the parity of the number of vertices. So this is another interpretation of tangent and secant number. But you will get some differential equations which are not the same as the one we get for alternating permutation. Y prime equal 1 plus y2, z prime equal yz. Well, once the one we get in chapter 3, this will be another differential equation. Another exercise, Jacobi permutation. So permutation sigma is called a Jacobi permutation if and only if for every value x or every vertex of the increasing binary tree, the world rho of x, remember the x factorization, and this word has even length.
Rho is the right factor, right?
Yeah.
Huh?
Right factor. The right subtree.
What do you say?
No, it's fine. The right factor in the subtree has the right subtree has.
The right subtree in the factor, yes, has even length. So call y and z the L species of Jacobi permutation on an odd numbers, even numbers, and show that they satisfy this differential system equation in terms of species. No, it's not too difficult. With initial condition, this is empty species. This is a species 1, the species which, and then you deduce that the genetic function satisfies this differential equation, which unique solution is again tangent 1 over cosine. So this system is not the same as the one we have done for alternating permutation. It was y prime equal 1 plus y2. In this system, the limit k, when you do k equal 1 in the system giving the three Jacobi elliptic function. I have given you a system of equation with three equations. If you put q equal 1, the parameter which define the Jacobi elliptic function, then you get this system. And from this system, from this Jacobi permutation, then you can get an interpretation of your Jacobi elliptic function. But you see, the philosophy is that each differential system of equation is related to a certain class of permutation, class of trees, and if you change the differential equation, then it will be completely different. It's not obvious at all that alternating permutations are counted as the same number as Jacobi permutation. It's difficult to find a bijection between Jacobi and alternating, but the exercise is to show that to each of these interpretations has a differential different system of differential equation. So we have now three interpretations: alternating, increasing 1-2 arborescence, and Jacobi permutation. Each one is related to a different system of differential equation. Even if trivially you can 1 plus y2, 1 plus tangent square is 1 over square of cosinus. Even by calculus, it's obvious that the functions are the same. But each one, when you do the interpretation, then you go to a completely different class of object. So we deduce that the number of assembly of increasing, so this is following the exercise, deduce that the total number of assembly of increasing arborescence on 1M shows that every vertex has an even number of child. Take arborescence, when the number of child of a vertex is even, then you get the total number of such object is secant number when m equal to n, is tangent number when m equal to n plus 1. So you can get a bijection with this class of permutation. So I give you the hint because on this big tableau relating arborescence, increasing tree, permutation, subextended function, I was taking the rotation on the left. So I think that you should take the rotation, the other rotation on the right, rotation changing a binary tree into forest of, or else instead of taking rho of x even length, you can take lambda of x even length. You can change rho to lambda, and so you have this hint for the exercise. Or I change rho and lambda in the definition of Jacobi permutation. And then you can deduce using species and assembly of this is assembly. This is of arborescence with even and odd. So you take off the root and you get this. So easily you can deduce this nice interpretation. So conclusion: we have three different combinatorial expressions of tangent secant numbers with alternating permutation, Jacobi permutation, 1-2 increasing arborescence, related to three different systems of differential equation. And in fact, there is, I mentioned when I show the picture of Schutzenberger, I mentioned André permutation. André permutation is very easily put in bijection with this interpretation, with 1-2 increasing arborescence are easily related to André permutation. So this is the zoo of tangent, secant, and all related objects. So now let's do a little of data structure and computer science. Last time we have a very glimpse of control theory, but now binary search tree. So when you have a permutation, you can define the binary search tree. In fact, it's defined for any word. You have any word, not only permutation. It's better to work at the beginning with distinct letters. And the binary search tree is the following. You start reading the first letters. Then you read the second letters. 6. 6 is bigger than 2. So we are going to put 2, 6 in the binary tree and with the right sum over 2. If 6 was less than 2, it will be on the left. Now I go to 4. I compare 4 to the root. It's bigger than 2. So I go here. I compare to here. 4 is less than 6. And so I put, now you put the 1. 1 is less than 2. See the rule. 5. So I compare to 2. Yes, less than 6, bigger than 4. So, and 3, bigger than 2, less than 6, less than 3. So you put the 2 here. So this is called the binary search tree. You are inserting your numbers in a binary structure, and this is done in computer science. If you have a list of people, of 1 million people, if you want to find somebody in the list, if you go from left to right, the mean will be half of the size of the list. But if you put the list as a binary tree, if the binary tree is more or less well balanced, then the average cost to find somebody will be in the logarithm of the number of elements in the field. So you have, and if the people is not in the list, you have to add the new guy, or add or delete. So this is very common structure, binary search tree. And what does it mean? That the property is that if you take the projection of this tree, you get the identity permutation. So in fact, when you look at this tree, you have lost completely the information of the permutation. Because if you give me a binary tree, you can put in so that the projection is identity. So binary search tree, in fact, it becomes a binary tree. But when we do the analysis of this algorithm, we are working on permutation. So if you want to recall the permutation, what you have to do is, in fact, each time you insert the blue numbers, insert the index in red, the index of the permutation. So this was the first element. Second element we have put in the data structure, the third, 3, 4, 5. So what you get is an increasing binary tree, the red value. So if you want to keep the information, initial information, to get the analysis of what is the average cost of inserting a value in the binary search tree, you have to keep this red value, and this red value is exactly the permutation you get in red by taking the projection. In fact, is exactly the inverse of the initial permutation. So the analysis of algorithm on the binary search tree is going to be an analysis on binary tree and increasing binary tree. So I'm going to show you a typical example, more difficult than the analysis of minimum. Minimum was, average was HN, the harmonic numbers. Now I would like problem. So problem means it's a sequence of exercise. It's 4 or 5 exercises which follow each other, and at the end you will get the average cost of an insertion in a random binary tree, and average cost with the minimum number of effort of calculus. Everything is bijective, and this is classical result in computer science. Usually they work with the calculus, but it's a nice way with all we know is bijection to do the and so you have a better understanding of what is this parameter. So the parameter is the number of comparison for the insertion of the last element. So you take a random permutation. So the analysis is above n factorial. And what is the number of comparison for the insertion? The last element in the... So this is exactly equal the height. This is the height of n in a random increasing binary tree. So the analysis of the cost for this binary search tree is equivalent to the analysis. Take a random increasing binary tree. Now we have seen the correspondence. Is this?
Last element?
Yes, the last one. You see here. Let's do, you see the last one?
Oh,
3.
3.
The last one, 3, is when you change into the inverse permutation, 3 was 6. Changing, because the increasing binary tree is exactly the indices of the value which are inserted in the binary search tree. So the last element inserted is the biggest value of the increasing binary tree. So I want the average height of the last element inserted in the binary tree. This is a key parameter for analysis of binary search tree. And I claim that this last element, this analysis, average cost, is exactly the average height of n in a random increasing binary tree. And the problem, the sequence of exercise, is to give a proof that the average, that this average height is the following 2 hn minus 1. So nice formula, simple. Hn was the average number of left to right minimum elements, so there should be a nice bijective proof of this formula to understand why is it twice shifted by 1 of the average number of left to right minimum element. So first, you start with the proposition that you have to prove that you take a permutation, you take the increasing related binary tree, you take a value x with any value, and then I want to have a characterization of the path starting from the root in the increasing binary tree until x. And I claim that this path is a union of the right to left minimum element of x1, x2, xi, union the left to right minimum element of xi, xn. See, x is somewhere in sigma, so you take the left part, everything which is on the left of x, take the right to left minimum element, everything which is on the right of x, take the left to right minimum element. So I claim that the path is this, and then I claim more that if you take any vertex y in the path, then I can characterize if y is belong, because this is disjoint except at the intersection x. These two sets are disjoint. So if y has a right child, if and only if it belongs to this set, and this belongs to this set, it's a left child. So I can completely characterize the right child and left child. I can characterize all the value between 1 and x. And here I put the particular case x equal n. This is going to be a particular case for the analysis of what we want to do. So take n equal 9. So this is the left part, x1, x2 until xi. This is the right part v. And take the right to left, so the right to left minimum element of this is 6, 1. The left to right minimum element of this is 7, 3, 2. And take the path, here going from 1 to n. So you see, in blue, you have 1 and 6. In blue, the vertex are, and in red, you have 7, 3, 2. 7, 3, 2. And 7, 3, 2, they have a left child. And 1 and 6 has a right child in blue. So I am here. And in red, I am here. So I can completely characterize my path by taking the union of these two blue and red elements, and blue and red give you where to go, left or right in the path. So this is the first proposition you have to prove in the exercise. And the example is the special case y equal maximum value n in my example here, but this is true for any, no, this is true for any x. Characterization of the path. So this path, you see, again, involves some outstanding element, left or right, and u in v. So we are coming to the HN, the harmonic numbers, the average of this. Now we follow the problem, second or third exercise. Define the map theta in the following. You have a permutation, sigma equal u and v. And theta of sigma, you replace n by 0. And reverse u and v. So I get a permutation on 0 and minus 1. If you don't like 0, you can shift everybody by 1. It's like a cyclic permutation on the indices. Then the vertices of the path going from 1 to n in the binary tree delta sigma are in correspondent with the left to right minimum element of theta and right to left minimum element of this. So in the following way, so this is the tree, this permutation, u and v. You reverse v and u, left to right and right to left becomes this. And this, we know from the previous proposition that this element corresponds exactly to the left branch and right branch of the binary tree. So think about that in the exercise. I go a little fast because it's an exercise not a part of the class. And then prove that the number of increasing binary tree on n, when such as that, so you have to take the union of the left branch and right branch, because you see what we have done here, combining the two propositions, is that my parameter is the height, the path going from 1 to 9, the height of n becomes the number of the sum of this red element and this red. So it becomes the length of the left branch plus the length of the right branch minus 2. I don't have to count the 0 twice. So you see the height of 9 is 0, 1, 2, 3, 4, 5. the height of 9 is 5, which corresponds to 3 on the left branch plus 2 on the right branch. So combining these two, my parameter become the length of the left branch minus 1 plus the length of the right branch minus 1. So now you have to show that this parameter, if you want the sum of the left plus right minus 2, the number of such increasing binary trees such that the parameter equal to k, which gives you the number of binary increasing binary trees such that the height of n is equal to k, this is exactly 2 power k Stirling number is n minus 1 k. And then the proof is you can do directly on the tree, or you can go back to exceedant function inversion table to get this proof. The idea is you have parameters, number of left to right, length of the left branch, length of the right branch. You are going to put everybody on the same side. But there is a color involving. The color is going to be the 2, which is here. Deduce the number of increasing binary tree, so that the height of k, n is k, is this. And then deduce that the average height of this parameter, now this is counted by n factorial, this, deduce that the average is this. You can use easily inversion table or so this is a nice combination of all you have learned in this class to get a nice result on the computer science, on data structure, the average height, average number of comparison in a binary tree. Okay, thank you very much. And